So remember, there's a bunch of derivations that you need to know that it explicitly says you need to be able to do, right? One of them includes being able to solve the gravitational field in terms of the radius and density of a planet, okay? It's never been asked on the AP test, but other derivations have been asked. So we have, I don't know if we have a long list, but there are different derivations that we've gone over, and at some point those will come up on tests. Okay, so make sure you know the derivation. So I'll go over this first derivation. It involves this equation here. Okay, so the gravitational field. So remember that on Earth, the gravitational force is just equal to what? If we use acceleration as lowercase g, what is the force due to gravity? Yeah, just little m times g. Okay, so what that means is that the general equation for the force due to gravity. Okay, so this is the general equation for two objects, is big G. I'm going to change M1 and M2 to uppercase M for the planet, lowercase m for the mass, and r squared. Okay, so this is an equation we've seen before. This is the force due to gravity between two objects. All right? The little m represents a mass on that planet. Okay, or near the planet. Possibly, yeah, absolutely. Okay, or just a person. All right. So the big M would represent the mass of the Earth. The little m would represent the mass of a person, and r would be the radius of the Earth.
Would it be the radius of the Earth, or the radius of the Earth, and the distance that it from?
Exactly. So that's actually going to come up as well on your. So make sure you guys understand that this r is the radius of the Earth plus any altitude above it. Okay, good point. All right, now, if I saw this little g here, this is called the gravitational field. If I solve for just little g, okay, the gravitational field, what would that equal from this equation? So all I got to do is get rid of the little m, right? What would that be then? What part is little g in this big equation here? Good. G big M over r squared. So that represents the gravitational field. Okay? All right. Now, the mass, so I can rewrite, so there's my equation. Okay? I'm going to rewrite the mass in this equation as m is equal to, I'm going to solve it for big M, so it's going to be the gravitational field times r squared over big G. Okay? So the density of so rho is the density of any object. The density of a planet would be the mass of the planet divided by its volume. Okay? I've rewritten the mass of the planet as being equal to G r squared over big G, like that. And the volume is a sphere, 4/3 pi r cubed. Okay? All right. And so this would essentially be rho is equal to, I'm going to put G r squared over G times 3/4. Let me know if I made a mistake. Pi r cubed. Okay? And we have to find what that's equal to. That would be 3G over 4 big G pi r. Okay? But if I rewrite that to solve it for G, the gravitational field, it would be equal to 4G. So this is just a bunch of algebraic manipulation, right? 4g pi r rho over 3. Okay, so once again, there's a bunch of derivations that you will need to be able to come up with by, given certain formulas. Okay, now the AP test, there is some history of saying be able to derive this particular equation from equations that are given to you. All right, so to be able to derive this equation, you obviously have to know that, and you would start off with this equation here. Okay. Obviously, you need to know the area or the volume of a sphere. So yeah, go ahead. Yes. So what I wanted to do is I wanted to rewrite. I didn't have to do that. I could have just solved for g and plugged rho into this equation based on, but I just wanted to make sure I can plug into, what did I wanted to do there? I wanted to make sure that my density was written in terms of m over v. I wanted you to see this equation written out like that. I could have written it out as m is equal to rho v and then plugged into there. So if you want to do it that as well. But most people are used to seeing densities, that equation first. Okay? Does that make sense? Yeah, just so just to make sure you understand. I could have started with this equation and then come up with this equation, but I would have had to solve this as m is equal to rho v first. Okay, rho v, and then plugged into there. Okay, and again, the reason why I wanted to solve it out that way is because I believe most students have seen density as mass over volume first. Okay, all right, now, I'm not going to give you guys any example. Yeah, go ahead. Literally, I would guess, it would, in some part of it, it would say, derive the magnetic field in terms of the density of a planet and its radius. I'm guessing it would give you more than that. Okay, I'm guessing it would give you the density equation, but I'm not 100% sure. So that's why I want to make sure you know that that's a density equation. Okay, we're gonna talk about this later on. This still works for an equation for a spherical object as long as the density is constant throughout it. Now, I think Jeffrey was going to raise his hand and bring up the fact that we're going to talk about the fact that we can figure out the gravitational force even inside a planet. Was that what you were going to bring up? Yes. Okay, as long as it's constant throughout. As a matter of fact, you can, from what I remember, Jeffrey, and it's in the back of my head again, this is coming up soon, is that you can figure out the gravitational field at some point inside a sphere, as long as it's completely uniform and constant, and you can ignore all of the mass further than that radius. Correct? Okay, we're going to talk about that later. Okay? Well, we're just assuming just the masses. Okay, you're right. We do not know exactly how gravity works. Okay, but we're just going to assume that that anything with mass, including the particles, exert gravitational force. Okay? All right. Now, so again, the equations, so for this particular assignment, I'm not giving you guys any examples. All right? You're going to go from these pretty straightforward equations and answering what I think are pretty easy questions today. Okay? So, however, you need to be able to figure out which of these equations to apply. All right? So, one of the equations that you will need to find is a relationship between the velocity and the radius of orbit of a satellite. Okay? And where we will start is with this equation, the force due to gravity equation, and we're going to set that equal to the centripetal force equation, okay? Because we know that for an object going, remember we made our list of all the different types of centripetal forces? For an object going around a planet, the centripetal force has got to be what? Gravity. Okay? So what we do is we'll set the force due to gravity equal to the centripetal force, mv squared over r. Okay? Where m is the mass of the object in orbit. That's the mass of the satellite. Okay, lowercase m. What I'm actually going to do is I'm going to set that equal to big G. I'm going to do the big M, little m thing again over, r squared. Okay? And I'm going to solve that for V. So if I solve this equation for V, this is what I get. I get V is equal to the square root of big G, big M over R. So this is a really important equation. This gives us a relationship of V in terms of R, okay, terms of R. Okay, so if you've got V for a satellite, you can find R because we know the gravitational constant and we know the mass of the planet. Okay? All right. With that being said, there's some other things we need to look at. Okay? Let's rewrite this equation. Let's square both sides of this equation and just look at this. V squared is equal to G big M over R. Okay? If I manipulate this equation so that the R and V are on the same side, I get R V squared is equal to big G big M. So what does that mean? What does that imply, this relationship? R V squared is equal to big G M. What does that imply for any radius and any velocity? What does that imply? Yes. R V squared is always equal to a constant. Okay? Big G and big M are a constant. All right, for any satellite. So we can actually rewrite this equation. Okay, so we know that this is a constant. Okay? So we would get R1. So if we had different, if we took a satellite and moved it from one radius to another, we can figure out its velocity. Okay? And notice that what really important thing about the satellite do we not even need? We don't even need to know its mass. Okay? So the radius, so what this tells us is the radius of a satellite, okay, depends on its what? Or we should say the velocity depends on its radius, right? I guess, yeah, should have written it that way. Depends on its velocity. Okay. So if you haven't written that right out, write down the velocity depends on its radius. Okay, not the mass. Okay. Yeah, they put that stuff on the multiple choice test all the time. Okay, especially in the B test. All right. Now another important relationship I want to look at is the centripetal acceleration. Okay, this equation here. Okay, we can combine that equation. We can combine this equation with that equation. Okay, and I can rewrite out the centripetal. If I plug the velocity into there, I get this. The centripetal acceleration is equal to v squared. So I'm just going to take 2 pi r over t. I'm going to square that and divide it by r. Okay? And I get 4 pi squared r over t squared. So double check my math there. Okay, so that's another way of writing out the centripetal acceleration. Again, this is for the object going around in the circle. All right, so all things that you need to be able to know. Now, this is in case you want the centripetal acceleration in terms of the period as well. Okay. All right. Now, let's also derive Kepler's third law. We'll talk about Kepler's laws later, but we're going to do the derivation of it right now. Okay. So Kepler's derivation, or the law of deriving his third law, goes like this. We know that velocity is equal to 2 pi r over t, but we also know that the velocity is also equal to the square root of big G m over r. We proved that in the previous page. Just like that. Okay, so I can set those two equal to each other. I can set 2 pi r over t equal to the square root of big G, big M over R. Okay? So to algebraically manipulate this, I want to square both sides. So I'm going to go 4 pi squared R squared over T squared is equal to G big M over R. Okay? So I get this relationship. If I cross multiply, I get T squared big G times big M is equal to 4 pi squared R cubed. Okay? And this says that this particular relationship, well, it says a few things. It says that T cubed, the period cubed, is proportional to the radius. The period squared is proportional to the radius cubed. And look again, if I do this, if I put T squared over R cubed, and this is going to come out to be pretty important later on, I get 4 pi squared over GM. Okay, so the right-hand side is a what? Is once again a constant. Okay, so we can do that thing again where we can set up T1 squared over R1 cubed is equal to T2 squared over R2 cubed. All right? And so this relationship is essentially Kepler's third law. But if we solve it for t, which is normally the way that people write it out, it becomes 4 pi squared R cubed over big GM, and I take the square root. So this is normally how Kepler's third law is written out. Okay? So there is precedence for this equation being asked on the AP test to derive. Okay? So to be able to derive that, obviously this equation needs to be memorized. Okay? And you have to be able to derive that equation from the stuff that we talked about on the previous page. Okay? And not only will you have to do that, you're also going to have to be able to apply that equation. All right? So there's another equation that you need to derive. Okay. Now, what I want to get into is I want to get just quickly into the total energy. Okay? Now, if we look down here, I've written the fact that the initial total energy should equal the final total energy for a planetary system. Okay? So each of those, E total, is going to equal the kinetic energy plus the potential energy. Okay? Now we know the kinetic energy, the total kinetic energy, is going to be equal to 1/2 mv squared. Okay? the gravitational potential energy's got a negative sign on it. Let's include that negative sign, okay? And there's a really important reason why it's got that negative sign. The reason it's got that negative sign is that we treat the gravitational potential as being 0 at infinity, okay? That makes the gravitational potential. Now, the gravitational potential is always relative to some arbitrary point. In this case, we're making the arbitrary point 0 at infinity. All right? Now, if you want to, we can spend some time later on going into why that's negative, but right now I just want to just kind of get you guys these equations because we're kind of short on time. All right? So, we know that, we know from our previous relationships, right, that this big M, okay, so this is something again, this is something that has precedence in a previous AP test. You need to know this. This big M is equal to V squared R over G. Okay? If I substitute that M into there, what I get is this. I get the E total is equal to 1/2 mv squared minus mv squared, okay, after canceling things out. And so I get the total mechanical energy as being negative 1/2 mv squared. Again, that negative sign has to do with our arbitrary choice of 0 of infinity being 0 gravitational potential. Let me finish this next part. Okay, then the V squared. This is from the previous, right? Then we saw that for as big M. Yeah, right there. If I solve, actually even before that, right? Right there, from that relationship, big M is equal to RV squared. Okay, so that's why all these derivations are so important. Yes?
So this is assuming that the sphere is not spinning, right?
This is, the mass. Yes. That's a good point. We would also need to include that. All right. Now, the other thing that you may be asked for is to write this in terms of R. Okay? So another way of solving this is if we say V squared is equal to big G over M, big GM over R, okay, and plug that into this equation, we would get E total as being equal to negative 1/2 big G, big M, little m over R. Okay? All right, make sure I double check my math on all this stuff. Okay? All right, so all derivations that you need to be able to do and all derivations that you need to be able to apply. Okay? Now, these equations, pretty straightforward. I will tell you the very last problem, I believe, that is on your equation sheet or is on your web assign is one of these two equations. I forget exactly which one. Okay, it's one of those two. What I'm doing is I'm just trying to help you with your web assign. The other really important equations, again, is this equation. Okay, you're going to have to apply that equation on your web assign. And you will also have to apply this equation a lot in your web assign. You have to know, not only be able to apply those, you'll have to also be able to derive them. In other words, be able to show where they come from. Okay? Some of the web assigns are actually so easy, you just find one of the equations on the left-hand side and just plug it in. All right? So, again, I'm not giving you any examples, but I will be coming around and help you guys out if you get stuck. I've got the WebAssign plan, a group quiz plan, and also a regular quiz. Okay, I made the timing of it. I think I've given 8 minutes for the regular quiz, and I think 5 minutes for the group quiz. Okay? All right, so go ahead. I'll come around and help you guys out. If you get stuck, please log on.